The next transfer function that we will consider is a transfer function that has a real zero not at the origin. And we can formulate this transfer function like this, where we have T6 of S is equal to 1 plus S over omega B. Again, omega B is called the break frequency. And whenever you've got a transfer function that has a real polar at zero, you should always try and write it into this form. I can give an example of a real transfer function that has a real polar at the zero at the origin, a real zero at the origin. For example, we can say, alright, well, something like this. And you should rewrite it into that form. You can factor out the 4, and then you can write it like that. So 4 in this case is our break frequency. Okay, to plot the frequency response, or the Bode plot of this transfer function, well, you will have to plot the frequency response of the constant 4, or the Bode plot of the constant 4, and then you can add this frequency response of the pole not at the origin to this frequency response. Again, you can do that because we are working or plotting in the log domain. Okay. Okay, to get to draw the Bode plots of this transfer function, we can rewrite this as 1 over 1 plus S over omega B. Okay, and again, because we're working or plotting in the log domain, what we can do is we can subtract this Bode plot, the magnitude and phase of that Bode plot, from the the Bode plots of the magnitude and phase of the constant. Okay. So we know that the magnitude plot of the constant 1 will just be a constant, or 0. Let's quickly try and draw that. Okay, so this is a decibel. Okay. We know for the constant 1, the magnitude is a constant 0 decibels. And we know for, well, let's use another color. We know that up to the break frequency for this part, the magnitude will be 0 as well, up to the break frequency, and then the magnitude will fall by 20 decibels, minus 20 decibels per decade. Okay. For the phase, we know for the constant 1, the phase is just 0. And we know for the pole not at the origin, we know that, well, the phase is 0 for up to 1/10 of the break frequency, and we know that the phase is -45 up to the break frequency, and we know that it is -90 for 10 times the break frequency. Okay. Oop. Okay. So to get the plots of the plots of the overall transfer function, we can just subtract the green part from the blue part. Okay. So up to the break frequency, both is obviously 0, so the result will also be 0. And then if we subtract the blue part, so let's say that's we see it's a constant of 0, then we subtract, let's say, this part, so let's call that v. So we see that, well, that's -v. We see that it's 0 minus -v, so that part will just become a positive. If we take that point, for example, and we call that some other value, let's say -w, then it will become 0 minus w, will become a positive w. So it will become there. So in effect, what's happening, the magnitude of a transfer function with a 0 not at the origin just becomes a reflection along this frequency axis. Okay, so that is the magnitude for okay. For the phase, well, we can see that both of them are 0 here up till 10th of the break frequency. Then at the break frequency, well, we take, let's call this value v, then it becomes again 0, because that for the blue it's 0 minus v, so it becomes a positive. Okay. And at 10 times the break frequency, that's a 0 for the blue, and let's call this -w, so it becomes a positive w. Okay, so again, in effect, the phase plot of a 0 not at the origin is just this reflection along the frequency axis. Okay, so now that you know how the Bode plot for a 0 not at the origin looks like, you can plot it directly.